This lecture is about environmental semantics and abstract machine E. The key concepts that we will be learning are environments and closures. Environments and closures. So let's first talk about environmental semantics. So previously we learned this evaluation judgment, a hook right arrow value V, which means that expression E evaluates to value V in a single big step. And the goal now is we'd like to exploit something called environment and eliminate substitution of this form V for X in expression E. So all the operation semantics that we have developed so far critically depends on this operation called substitution. We have to have this substitution in order to reduce a regex of this form. But now we'd like to eliminate this substitution by introducing something called environment. The idea is that instead of performing this substitution right away, we'd like to carry this environment, which contains a mapping of this form, X, hook right arrow value V. So whenever we encounter a substitution of this form, we just keep evaluating expression E, and we augment the environment with this new mapping. So we remember the fact that X should be replaced with the value V, and we do not perform the substitution right away. So if we have V for X in E, instead of performing substitution right away, we just keep evaluating expression E with an environment that contains this mapping, X hook right arrow value V. So later, when we actually encounter variable X, we look up this environment and retrieve the value V, and at this point, we actually perform substitution. So we do not completely eliminate the substitution, but instead, we actually postpone the substitution as much as we can, and we perform this substitution only when necessary, only when we actually encounter this variable X. So that's the informal introduction to this idea called environment. So here's a formal definition of environment. So we define environment as a new syntactic category, and we use this meta variable eta, which is defined as either an empty environment or an existing environment eta extended with a new mapping X hook right arrow value V. So this mapping means that the variable X is supposed to be replaced with value V. We just didn't perform the substitution when we encountered the substitution operation. We just remember the fact that this variable X should be actually replaced with this value V. So that's the definition of environment. Now we introduce new form of a judgment, which is called environment evaluation judgment. So it's evaluation judgment, so it has this form, expression E, hook right arrow, value V. But in addition, we carry this environment all along. So that is, we augment this judgment with this environment. So this is the new form of evaluation judgment. Environment evaluation judgment. It's evaluation judgment because it has this big step. It uses this big step style, But on top of that, we carry this environment. So it's called environment evaluation judgment. So what that means is that under this environment eta, expression E evaluates to value V. That's the interpretation of this new form of judgment, environment evaluation judgment. So let's consider a small example. Suppose that we start with an empty environment, and let's assume that we are about to perform this substitution, true for x, in this expression, E1 else E2. So we'd like to evaluate this one to produce some value V here. In the previous big step semantics, we perform substitution right away. So we locate every instance of a variable x. Here we have one instance, and this expression E1 and expression E2 might also contain lots of instances of variable x. So we have to locate all such instances of a variable x and replace them with the value true at this stage. But that's not the way that we evaluate the expression now, because now we exploit this environment. So instead of performing substitution right away, we postpone the substitution as much as we can. So what we do is we extend the environment. Currently we have an empty environment. Now we have this singleton environment. So this mapping says that we have to replace this variable x with value true. So later when you evaluate this expression and encounter variable x, we go back to this environment and retrieve the value and then use this value true for this variable x. So because we have extended this environment, we copied this expression as it is and then try to evaluate. And this is if then else conditional expression. So we have to evaluate this expression. So the next step is going to be, under the same environment, we want to evaluate this variable x. Now we find that the expression under evaluation is actually this variable x. If we had performed substitution in the previous step, this variable x would have been replaced with the value which is true, but we didn't perform the substitution previously. So what we do is we go back to this environment and find out the corresponding value, which is true in this case, and then retrieve it. So notice that instead of performing substitution here, we just look up the environment. So in some sense, the substitution here is postponed, and later we actually just perform this lookup operation. We just look up the environment to retrieve the value. So this is the way that we evaluate variable under this environment evaluation judgment or environment semantics. So now we have decided the value for this variable x, so it's true, and we want to evaluate the expression E1 by taking this then branch. And in general, this expression E1 might also contain this variable x, so we have to copy this environment, not just here, but here as well. So the environment under which expression E1 is evaluated is the same environment x true. Suppose that this one produces some particular value v, then this one is going to be v, and the final result will be also value v. But that's pretty much the key idea behind this environment evaluation judgment. So the idea is instead of performing substitution right away here, we carry this environment which contains all the mappings for all variables. And when we actually encounter a variable, so like here, then we look up the environment and retrieve the value. So in this way, we postpone the substitution, and in some sense, we just replace the substitution with environment lookup. Instead of performing substitution, we just look up the environment. So things are much simpler. And moreover, let's assume that this expression e1 and e2 are both variable x. So this one is variable x. Variable x. So if we perform substitution in the previous style, we have to replace this variable x 3 times, this one, and this one. But if we take advantage of this environmental semantics, what happens is we replace this variable x only when necessary. So in this particular example, this variable x is evaluated to true. So it turns out that we will later substitute true for this variable x, but we will never analyze this expression, this variable x. So we also gain some efficiency in evaluating the given expression by avoiding unnecessary substitution. So that's the idea behind all these environment and environment evaluation judgment. Now let's develop the inference rules for this environment evaluation judgment. So we have the definition of environment, which is entity or environment eta extended with this new mapping, and the judgment is eta turnstile expression E, hook right error value V. Now let's develop the inference rules for this one. So this is the first attempt. Suppose that we'd like to evaluate the variable x. In the previous formulation of operator semantics, this variable x has already been replaced with some value when we perform the substitution. But here, we have to look up this environment. So we look up this environment eta, and suppose that we find this mapping in this environment eta, then we take the value v here. So that's how we evaluate the variable. Next, let's say we want to evaluate this lambda abstraction. Our first step is we just return the lambda abstraction itself. And what about the application? Under environment eta, we evaluate the expression E1 applied to E2. So if this expression is well typed, perhaps this expression E1 will produce this lambda abstraction, let's say lambda xa.e, and then we evaluate expression E2 to produce value V2. Now remember that we do not perform substitution. We just carry the environment. We extended the environment and keep evaluating this expression E. So previously, we substitute this value V2 for variable x in the body E, and then we will evaluate this expression. But now, we do not perform substitution. Instead, we extend the environment eta with this new mapping, x hook right arrow value v2, and then with we would evaluate the expression E. If this guy produces value V, the final value would be also V. So that's the idea. And what about true? Well, it's easy. True, just return the true. And there is the other case for false. And what about this if then else expression? If expression E, then E1 else E2. We have to evaluate the expression E. So let's say this one produces a true. Then we take this then branch. So evaluate the expression E1 to, let's say the result is value V, then the whole expression evaluates the value V. And there's a symmetric case for taking the else branch. But this is our first attempt, which implies that there's something wrong with some of these rules. So all these rules look quite innocent, but there's some serious flaw in the design of some of these inference rules. And it turns out that, first, this rule is definitely wrong. Intuitively, let's consider this lambda abstraction paired with this environment. Remember that when we evaluate a variable inside expression E, we have to go back to this environment to retrieve its value. So if you just put this, if you just isolate this lambda abstraction, there's something that we cannot do, because when we later evaluate some variable, free variable, to be some free variable in expression E, there's no way to evaluate it because environment is missing. In order to evaluate the free variables in the expression E, we have to carry this environment as well. So if you just return this lambda abstraction, something is missing. That is, we now lose the access to these free variables. We can no longer retrieve the values for the free variables. So there's something wrong with this rule. Then how can we remedy this design flaw? The intuition is, in order to evaluate the expression E here, the body of this lambda abstraction, you have to carry this environment so that you can resolve the free variables in the expression E. So for that reason, it's not enough to return this lambda abstraction only. You have to actually return this environment as well. So it turns out that the result of evaluating this lambda abstraction under this environment eta is a pair of this environment and this lambda abstraction. And the reason that we carry this environment is so that we can resolve the free variables in expression E. Without this environment, there is no way to evaluate the free variables in expression E. So that's the reason. Now, we always return this environment along with this lambda abstraction. So we pair them up. And this pair is called closure. So closure is basically first class, the representation of first class function. It's a function, but without this environment, there's no way to evaluate the free variables. But in the presence of this environment, we can think of this lambda abstraction as closed. because free variables can be replaced with variables found in this environment. So in some sense, from the perspective of an outside observer, there's no free variable. All these free variables in expression E can be resolved somewhere in this environment eta. So that's the reason that this pair is called closure. So it's called closure. And now this is new form of value. So previously, values V has this lambda abstraction and true and false. Now, this new form of value, closure, which is a pair of this environment and lambda abstraction. So this is environment paired with this lambda abstraction. This is new form of a value. And there's one slightly complicating factor here, which is now expression E put right at value V. Now this expression E and this value V belong to different syntactic categories. Before we introduced this closure, this expression E and this value V belonged to the same syntactic category, namely expressions. In other words, this value V was just a particular form of expression E. But that's no longer the case because now the definition of values is completely different. We have this new element called closures, and this closure is not an expression. Syntactically, it's not an expression, valid expression. It's just a new form of a value. Now, in this environment evaluation judgment, remember that this expression E and this value V belong to different syntactic categories. So we have fixed the bug in this rule, and the fix is we have to return not just this lambda abstraction, but also we have to return this environment. And by pairing these two guys up, we obtain something called closure. Now let's fix this application rule. If everything goes all right, if this expression E1 applied to E2 is well typed, this expression E1 now produces not just a single lambda abstraction, but instead it returns a closure. So it returns eta prime, this lambda abstraction. Notice that this environment is not necessarily the same as this one, which implies that we can actually create new functions on the fly when we evaluate an expression. So in general, this environment is not the same as this one. So we have to use different meta variable. So here we use eta prime. So the result of evaluate expression E1 is now this closure. Suppose the expression E2 produces the value V2. Now it's time to make a function call. So we have this function lambda abstraction lambda x dot e, and we have its argument. So in the previous formulation of operator semantics, we would perform substitution at this stage. But the key point in developing this environment-based semantics is we postpone the substitution. So instead of performing substitution at this moment, we just keep evaluating the body, this expression E. So we evaluate expression E. Then the question is, what is the environment under which expression E should be evaluated? But let's go back to the interpretation of this closure. So this closure means that all free variables inside expression E can be found in this environment eta. That's why this new form of value is called closure. It's essentially closed from the point of view of an outside observer. So in order to evaluate expression E, it suffices to carry the environment eta, because all the free variables in expression E can be found in this environment eta prime. So in order to evaluate expression E, you do not want to use this original environment eta. Rather, you want to use this environment eta prime that is associated with this lambda abstraction. So, so this expression E comes from here. So the environment must come from the same closure. And in addition, we have to do something about this variable x, because currently this variable x is not accounted for. So we want to extend the environment with a new mapping x, hook right arrow, value v2, because v2 is going to be the argument for this variable x. So x is now mapped to value v2. So to summarize, in order to evaluate the expression E, you want to use the environment found in this closure, and then extend the environment with a new mapping. The mapping from this formal argument, variable x, and the actual argument, value v2. Now, every variable inside expression E, every free variable inside expression E can be accounted for by looking at this environment. It's either those present in eta prime or the new variable x. So now we can safely evaluate the expression E. So this is how we fix the bug in the previous attempt. So the key difference is this expression E1 returns not just this lambda abstraction, but also returns the environment for this lambda abstraction in the name of a closure. And when we evaluate the body, you have to use the environment associated with this lambda abstraction. So that's the idea. But that's how we fix these two evaluation rules. So that's the operation semantics, yet another operation semantics for this environment evaluation judgment. Now we have developed inference rules for this environment evaluation judgment. And what is the key idea? Key idea is use environment eta. And why do we use this environment? To postpone the operation of a substitution. So every time we encounter this substitution, we just extend the current environment with this new mapping. So in this way, we just carry this environment and we look up the environment only when necessary, when we encounter some free variable. So that's the idea. So it's one step closer to a realistic implementation of the operation semantics, where we don't actually perform substitution in a naive way. Instead, we manipulate this environment for efficient implementation of the substitution operation. So that's the key idea. Now, let's combine this idea of using environment with the idea of abstract machine C. So what was the idea behind the abstract machine C? So in abstract machine C, which actually is based on the idea of evaluation context, the idea was that we'd like to make it explicit to analyze the structure of given expression. We have an expression E, and inside this expression E, we have some radix. And this abstract machine C makes it explicit how to reach this radix. So we introduce two states, something like a sigma right triangle expression E, which means that we are currently analyzing the structure of expression E to locate such a radix like this one. And there's another state which is sigma left triangle V. We have finished evaluating expression E and now returning this value V as the result. So that was the two states in abstract machine C, and the idea was with this state transition rule, now we can systematically locate the radix to be reduced at the next step. So that was the idea behind the abstract machine C. The plan now is we'd like to combine these two ideas, the idea of using environments, which allows us to, this idea allows us to practically eliminate the substitutions, because we can postpone these substitutions until when necessary. So it's going to be very efficient implementation. So we'd like to combine this idea of environment or closures with the idea of abstract machine C. And the result is going to be something called abstract machine E. In abstract machine E, we will carry these environments all along so that we can postpone substitutions. And similarly to the abstract machine C, we will systematically analyze the given expression to find the radix. So let's develop this abstract machine E. So similar to abstract machine C, this new machine, abstract machine E, also has two states. So state is either sigma is still the step of frames. This is whole or an existing stack extended with frame phi. This is a stack. This is a frame phi. And we have two, this is a state, and we have two states. The first is under stack of frame sigma, we are currently analyzing expression E. So this is the first form of a state, and or we are returning value V produced from perhaps this expression E. But what's new in this abstract machine E is the user environment. So we have a new component here at environment eta. So the interpretation of the first state is we have accumulated this stack of frames so far by analyzing the structure of a given expression. And we are currently analyzing, so this right triangle, just like abstract machine C, this right triangle means that we are currently analyzing the expression E under this environment eta. And this one means we are currently returning value V back to this stack of frames. Now, we have to develop the state transition rules. So state transition has this form: state S transitioned to another state S prime, and we'd like to develop the state transition rules. And remember that because we use environment, this environment values now have this closure environment lambda x a dot e, or it's true or false. So let's develop the state transition rules. It's just like the exercise that we previously had when we developed abstract machine C. So it's also fun to develop the state transition rules, and it's also quite a nice educational exercise. So I encourage students to take on this problem and try to develop the state transition rules on their own. So and by developing the state transition rules, we can actually fill the definition of frames here. So let's figure out what kind of frames we would need in order to complete the design of this abstract machine E. So the first rule is, suppose that we are currently analyzing this variable x under environment eta. So what should we do? So there's nothing we can do about this variable x without accessing this environment, because the value for this variable x is presumably found in this environment eta. So this is basically the time to look up this environment and retrieve the value for this variable x. So let's assume that this mapping x value v is found in this environment eta. Then what happens? Well, we have found the value for this variable x, so it's time to return the value back to the stack of frames. So now we return, so it's left triangle, this value v. So that's the rule for this variable. Next, what about the state transition rule for lambda abstraction under environment eta? So we have seen the proper way to deal with this lambda abstraction when we discussed the idea of closures. So the answer is we have to perhaps create a new closure and return the closure as the value, as indicated by the component of this component in the definition of values. So it's time to create this closure. So let's create a closure, and closure is a value. So let's return this value called closure. So we build a closure here. The second component is, of course, this lambda abstraction. And what is the closure? This environment contains everything you need in order to resolve the free variables in expression E. So of course you want to use this environment data. Now this one is practically closed, so it's called closure. Now let's see the most complicated case, which is of course application. Suppose that we are currently analyzing expression E1 applied to E2 under environment eta. So in the case of abstract machine C, we don't need this one, and the next state would be sigma. This is a whole expression E2, and we keep analyzing expression E1. the reason that we leave a hole here is later, when we return some value v1 produced from expression e1, we'd like to fill this hole with this value v1 and then continue to analyze the expression e2. So that was the way that this state is dealt with in the abstract machine C. Now things are slightly different because we have environment here. So it's a time to analyze expression E1. So we would leave behind this frame. So this is a new form of frame. And we would like to analyze expression E1 under the same environment eta, because this environment eta applies to both expression E1 and E2. In other words, this environment is effective in the scope of this expression E1, E2. So when you analyze expression E1, you of course wanted to use this environment eta. But there's something missing here, which is if everything goes all right, we will return some value v. Let's say v1 produced from this expression E1. Then we would have something like this one. Then we would analyze the expression E2. The question is, what is the environment under which expression E2 should be evaluated? It is eta, right? So in other words, this expression E2 should be analyzed under environment eta. So we have to remember the environment eta somewhere in this frame. And the trick that we employ is we annotate this hole with eta. So that later, when this guy returns a value v, we can restore the environment eta by looking up the annotation in this hole. So that's the reason that we'd like to annotate this hole with eta. So we have figured out the first component in the definition of a frame, which is hole eta expression E2. Not just the expression E. So that's the first component in the definition of a frame. Now, suppose that everything goes all right, and we produce something like sigma. This is eta expression E2. Now, this one produces perhaps some closure. If this expression is well typed, so we have some closure here, eta prime lambda x a dot e. So how should we reduce this one? It's time to analyze this expression, the argument. So the step now is this one, eta prime lambda x a dot e, and we leave a hole here. This hole indicates that we are currently analyzing expression which is E2 that was in the position of this hole. And what is the environment for expression E2? We decided to leave the environment as an annotation of this hole. So we make a copy of this hole here. So we have found the second form of frame, which is this one. So it's going to be closure lambda xa dot e with a hole. Now suppose that everything goes okay again, and we produce the value v from this expression E2. Then we would have something like a sigma eta prime lambda x a dot e whole, and we are currently returning this value v. Then what is the next state? So in the case of abstract motion C, it's time to perform substitution. But we don't have substitution. Instead, we just carry this environment all the time. So now we have this lambda abstraction and its argument. So we'd like it to evaluate this expression E. So it's a time to evaluate expression E. The critical question is, what is the environment? So let's recall that this closure contains everything that you need to evaluate this expression E. So because we are currently analyzing expression E, we have to restore this environment eta prime, of course, along with the new mapping that accounts for this variable x. So the new mapping is going to be variable x mapped to the argument value v. So that's the new rule. Finally, there are several rules that we need for this Boolean type, but let's just see the most interesting case, which is let's reduce this if then else expression. If E then E1 else E2 under environment eta. So the scope of this environment eta applied to all these three expressions: expression E, expression E1, and expression E2. So we are going to analyze expression E because we have to decide if this is actually true or false. So we are going to analyze expression E. But when we return, we will take either this then branch or else branch. So we have to leave the frame here. So if whole, then E1, else E2. So this whole indicates the position of the expression that was the position of the expression that is being analyzed. But similarly to the lambda application, when we come back, we will either choose expression E1 or expression E2. And we have to also remember the environment for these two expressions. So somewhere we have to store the environment eta for expression E1 and expression E2. And our trick is we annotate this whole with the environment eta for this expression E1 and expression E2. So this is the answer. And the environment for this expression E is, of course, this one. So we have discovered the last form of a frame, which is if whole, then E, else E, and we annotate this whole with this environment eta. Now suppose that everything goes fine, and we produce, let's just say, Boolean true from this expression E. Then later we will have something like if eta then E1 else E2, and now we are returning the value true. Then what is the next state? So this is a Boolean true, so we are going to take this then branch. So we will analyze expression E1. The question is, what is the environment under which expression E1 should be evaluated? And it is, of course, eta. And that's the purpose of this annotation, the environment for expression E1 and expression E2. So we restore this environment eta and keep evaluating expression E1. And the case for Boolean false is, of course, we evaluate the expression E2.